All right, in today's lesson, we're going to be looking at the irrational number e. What we have here to the left-hand side, this is some, not all, of the digits of this irrational number. Again, because it is irrational, this sequence will never end. And you can see here the first several digits of the irrational number e are 2.7182, 8182, etc., etc., etc. To the right-hand side here, I just have one representation of e. E can be expressed as the summation, as n goes from 0 to infinity, of 1 over n factorial. We'll leave that proof for another lesson. But our goal for today's lesson is to discover, where does e come from? Can we get an intuitive idea as to what e actually is? And through that, we'll understand why it is called the natural base. And we'll look at some application questions and results that come about from deriving and working with this natural base e. Let's get started. All right, to start us off here, I have a familiar formula here. This is the formula for compound interest, where P naught was the amount of your initial investment, 1 plus I. I was defined to be equal to your rate of interest, R, divided by the number of compounding periods, K, in a fixed year. And T was the number of years you're investing for. So using this compound interest formula, we will use this to derive the irrational number E. Let's take a look at some assumptions we have to impose on this formula to find this irrational number e. So you'll see here what you want to do is, first of all, we're going to assume we're investing $1 for 1 year, and we're going to assume that annual rate of interest is 100%. So essentially what we're doing is my P naught value will be 1, my I value will be 1 divided by K. Again, we put a 1 there because I'm assuming a 100% rate of return, and we're going to do this for exactly 1 year. Under all of these assumptions, our P at T formula for compound interest reduces to just become 1 plus 1 over K, the entire expression to the value of K. This represents my total account balance after investing $1 for 1 year at 100% interest if it is compounded K times. So what we have here to the left-hand side here, you see I have a table. And for the first situation here, I'm letting K equal 1. And if K equals 1, we're compounding at the end of the year. So you just double that amount at the end of the year, and you have yourself $2 instead of $1. In the second situation, what I'm doing here is I'm letting K equal 2. So now we're compounding semi-annually. So if we go ahead and take this formula here, and I let K equal 2, we're going to end up getting here, you'll see you end up getting 1 plus 1 over 2 squared. And if you do your calculation on that, you'll find out that comes out to be 9 over 4, which is exactly $2.25. So again, as we move along this chart here, we let K be 4 and K be 12. You can see your approximate account balance is starting to cluster towards a number. And you can probably guess what that number is going to be. That is clustering towards the irrational number E. So as my K value approaches infinity, i.e. the number of compounding periods becomes continuous, right? In this situation here, we're going from annual to semi-annual to quarterly, monthly, daily, hourly, by the minute, by the second. If you let this go to infinity, you're now computing interest continuously, and it turns out that this expression here will tend towards our irrational number E. All right, so now that we've let K go to infinity and we've now created this irrational number E from this computation here, this 1 plus 1 over K to the power of K, this deals with continuous growth. So now whenever we're talking about something that's growing continuously, whether that becomes investments or possibly talking about population growth as well, there's many applications of this. When that is continuous growth or continuous decay, the model that is used incorporates a base of E. This base is also referred to as the natural base, as it does occur in many real-world problems. Just to give some credit here, we have Euler discover this in 1772, and as discussed, it is called the natural base. I've just graphed y equals 2 to the x and y equals 3 to the x, and just to show you that y equals e to the x lies in between, it's going to be tighter and closer to your y equals 3 to the x function because, again, that base value is 2.71, etc. So it is closer to the base of 3, and you can see it is steeper and kind of tending towards this y equals 3 to the x function. So just to summarize some of the findings that we have is whenever you have these exponential functions and they're represented with a base of e, that references continuous growth or continuous decay. So the idea here is if your k value is greater than 0, that's going to represent growth. If it's less than 0, i.e. a negative value, we are talking about decay. The k value itself is referred to as the growth rate, the continuous growth rate. So therefore, any population, for instance, or anything that you're looking to model, if it has a base of e in it, that is referencing continuous growth or continuous decay. Let's take a look at some application questions dealing with this growth model. All right, so in our first example here, we have a population increases from 7.3 million, and they say in the question has a continuous rate of growth. So as soon as you see that word continuous rate of growth, we know it's referencing my continuous model we've just derived. That's happening at 2.2% per year, and they want you to write a formula to represent the population after t years. Well, our formula here would be the population at time t is going to equal p naught e to the kt. But now we know some of these values here. I know that p at t is going to equal p naught represents my initial amount. So what do we start off with in this problem? Well, in this problem here, we're starting off with 7.3 million. Now you could either write 7.3 million explicitly with all the zeros, or just write it as 7.3 and assume your final answer is measured in millions. They tell me I have a continuous rate of growth of 2.2% per year. Again, that must be written as a decimal place, so we're going to take that 2.2%, divide it by 100, and that's my k value, and then we multiply by t. So what we have right here, this represents the population at time t, which starts at 7.3 million and is growing at a continuous rate of 2.2% per year. In the next example here, we have caffeine is leaving the body at a continuous rate of 17% per hour. And what they want you to do here is how much caffeine is left in the body 8 hours after drinking a cup of coffee containing 100 milligrams of caffeine. So now this represents continuous decay. And in this example here, we would have p at t is going to equal my initial value, what I'm starting off with, so that'll be 100, times e. My k value here is going to be negative 0.17. So again, how I got that was I took my 17% and divided by 100. And then because it is leaving, they use the word leaves the body. We know that it has to be a decay function. So I had to multiply that by a minus sign, and then that's for a given time t. So in this question, they want you to assess this after 8 hours. So therefore, since t is measured in hours, we're going to evaluate this at 8. This will be 100e to the negative 0.17 times 8. Calculating this, we get an approximate value of 25.67 milligrams. All right, so that was our introduction to the irrational number e. I just want to show you and give you an intuitive understanding as to where e comes from, one example of how it can be derived, and then that does lead to this idea of our growth and decay models. The p at t is p naught e to the kt. And then we can go ahead now, and I've shown you two quick little examples of creating those models. Please take a look at the next lesson where we take a look at this model and apply it to various situations, one of which is continuous interest. Thank you.